Hey guys, welcome to day 2 of Trig review. This day is to review special right triangles. We talked about this, we learned this back last year in geometry, so hopefully it does kind of ring a bell, but that's going to be the focus for today. So our two special rights are called 30, 60, 90 and 45, 45, 90 triangles. So we're first going to talk about where these two even come from. And then we'll go through some examples that show you how this is useful for us. So, starting with the 30, 60, 90 triangle, here we have an equilateral triangle. And this equilateral triangle has, since all the sides are equal, the angles are also going to be equal. So if you remember from geometry, all three angles of a triangle add up to 180 degrees. So when you divide that by 3, you get an even 60 degrees per angle. Now for convenience sake, we're going to go ahead and say that every side length of this triangle is a length of 2. All right, so now that we have our triangle to work with, we're going to go ahead and chop it in half. We're just going to take this whole triangle and cut it right in half down the middle. By doing this, we've created two right triangles, one on the left and one on the right. It's kind of uneven. All right. So now we're going to go ahead and focus in on one half of this triangle, and that's what I've drawn for you here. It's kind of a mini version, but what we're doing is we're kind of zooming in on this left half of the triangle. So we want to find out all of the sides and angles of that triangle. So we'll start with the angles. We know that this bottom left corner is 60 degrees. We already know that this one right here is a 90-degree angle because when we drew that height, it was perpendicular to the base. But this top angle, because we took this original triangle and just chopped it in half, that top angle, which used to be 60, also got cut in half, and now it's 30. Okay, and that's where the name 30, 60, 90 triangle comes from. When we cut an equilateral triangle in half, straight down the middle, we get a 30, 60, 90 triangle every time. So we know that the side, the longest side, based on what we're looking at in the original, is going to be 2. Right, because that side was not altered at all. But the base here, it did change. So if we look at the original base of our equilateral triangle, it was 2. So when we chopped it in half, the one side of it ended up being half of 2, which is just 1. And that leaves us to find out what this side is. Now that's the height of the triangle, and we don't know any information about that yet. However, we can use the tools we talked about yesterday to find it. So that's where our Pythagorean theorem comes in. Okay, so we know that the longest side is always C, and we know that the other two sides are just A and B. Okay, so it doesn't matter which is which for A and B as long as C is correct. So now we can set up our formula. We know it's A squared plus B squared equals C squared. So we just plug in. Instead of A squared, we have 1 squared. Instead of B squared, well, just kidding. B squared stays B squared because we don't know what B is. But instead of C squared, we're going to have 2 squared because our C is 2. So now we go ahead and simplify and solve for my B. So we know 1 squared is 1, B squared still doesn't change, 2 squared is 4. And we're on a journey to get B by itself. So this one needs to move. We'll subtract it from both sides. So we end up with B squared equals 3. At this point, we're very close to solving for B, but we're not quite there yet. We've got to get rid of this square, and hopefully we know that to do that, we have to do the opposite, which is to square root. So that tells me that my B length is equal to the square root of 3. Now we're just going to go ahead and leave it like that. Okay, so we know that B is the square root of 3. All right, So we are going to go ahead and talk about how to use this in the examples below a little bit later. Let's now go ahead and talk about the 45, 45, 90. So the 30, 60, 90 originated from cutting an equilateral triangle in half. The 45, 45, 90 triangle comes from cutting a square in half. So let's go ahead and cut this square in half and see what that does for us. So we're going to cut it in half diagonally to create some triangles. Now, we know that a square has 4 right angles. All right, so this is a right angle, it's 90 degrees. That line is slanted. There we go. Right angle, and right angle. So we know that originally all those angles are 90 degrees. And so when we cut our square in half, these two right over here on one triangle turn into 45-degree angles. Right? So now we're going to go ahead and zoom in on one of those halves. Down here I have created that half. It's a little mini version. So we know that these two angles are 45 degrees. And this one is still 90 because it was untouched. Now, just like how we picked a convenient length, side length for the equilateral triangle, we're going to pick another one for this one. This time, our convenient side length is going to be 1. So every side of this square has a length of 1. So keeping that in mind, in my little half of the square here, this triangle, these two legs are going to have a length of 1 as well, because it's just these two. And we have to figure out what the third one is. So that's where my Pythagorean theorem comes into play. We know that we're solving for the longest side this time, so we have a C we're looking for. And we already know that these two legs are going to be A and B then. So now let's set up our Pythagorean theorem. Again, it's a squared plus b squared equals c squared. So we plug our information in. Instead of a squared and b squared, we'll have 1 squared for both of them because they're both the same. So now we have 1 squared plus 1 squared. That's just 1 plus 1. And that tells us that c squared is equal to 2. So just like the last step in here, we need to get rid of that square by square rooting. So that tells us that c is equal to the square root of 2. All right, so here's the deal. Now we have all the information about these like prototype triangles, and these are going to be the basis for what we use when we're trying to figure out new triangles that are still these same angle measures. So let's take a look at this first example. This one has a 90-degree angle right here and also a 30-degree. Hopefully you would realize that if there's a 30 and a 90, the other angle has no choice but to be 60, because remember they all have to add up to 180, and if you hear 30 and 90, you should be like, oh well, that's going to be a 30, 60, 90. So I know that this is a 30, 60, 90 triangle. And then I have to look at the proportions. Now hopefully from geometry you remember that two shapes that have all equal angles are actually similar. And what that means is that all the side lengths are in proportion. So if we know that this particular 30, 60, 90 triangle is in proportion to this 30, 60, 90 triangle because of the equal angles, we can find a scale factor and use that to find the other two sides of my triangle. So here I have that the shortest side, the side that's across from the 30-degree angle, is a length of 10. Now on this triangle, the side across from the 30-degree angle, which is the shortest side, is 1. So that tells us that my new triangle is 10 times as big as the original one. This is what I'm referring to this as the original one. So we know it's 10 times, well, I'll just write that, 10 times as big. So that means that we can take every other side of this triangle and multiply it by 10 to get this triangle, because that's what we did for the first side. So for x matches with 2. So because it used to be 2, we just multiply that by 10. And we find out that this side is 20. X equals 20. For y matches with this square root of 3 sides, so we just have to multiply square root of 3 by 10. Okay, and again, the reason we're multiplying by 10 is because we found out with this original one being 1 and the new one being 10, that means it was multiplied by 10 to get from the original to the bigger one. Okay, so we found that x equals 20, y equals 10 root 3. And we want to just leave it like that. We don't want the decimals. All right, so that's how you do this first one. My next one, hopefully you would recognize, is a different kind of triangle. There's a 45-degree angle and a 90-degree angle. That means this one has to be 45 degrees. And surprise, surprise, we have a 45, 45, 90. So in this one, what's nice about the 45, 45, 90 is that the two legs are always going to be the same because these are always isosceles triangles. So right away, you already know that this leg is going to be equal to this leg. So it's going to be 4. But it's important to recognize that there is still a scale factor here. If the legs were originally 1 and the new one is 4, that means we're 4 times as big. I'm going to go ahead and write that it's a 45, 45, 90. And we are 4 times as big. So I also could have taken this 1 and just multiplied it by 4 to get the other leg. And then for the other last leg, we are originally root 2. So my new one is just going to be 4 times that. Okay, all I did was I found the scale factor and I multiplied all the sides by it. All right, and that's it for that triangle. So we found out that x is 4 and y is 4 root 2. All right, my last triangle. So now we have a 60 and a 90-degree angle. So we should know that this last one must be 30. And so we're working with the 30, 60, 90. Now, this one, we've been given the long side, which is 6. In the original 30, 60, 90 triangle, the long side was 2. So if we do 6 divided by 2, we get 3 for our scale factor. So that tells us that this triangle is 3 times as big as the original one. Okay, and then we found out that it was a 30, 60, 90. I'll write that too. All right, so now we just have to take my original 30, 60, 90 and multiply all the sides by 3 to figure out the sides of the new one. So y matches with the 1 here, so 1 times 3 is going to be 3. That's our length of y. And then x is going to match with the square root of 3 sides, so square root of 3 times 3 is just 3 root 3. So my x is equal to 3 root 3, and my y is equal to 3. And we've solved it. So the whole point of this is just to have a shortcut so we don't have to do right triangle trig or Pythagorean theorem every single time. We can just use scale factor and these original prototype triangles. All the problems that you're going to do in My Open Math are going to be using these same 2 triangles, so you might want to write them down or something. so you can refer to them later. But that is all for today. Give the open math problems a try and let me know if you need help.